All right, ladies and gentlemen, hello. We're going to talk about colligative properties, which means that we're going to talk about how how the structure of water changes as we add things to it. And let's talk about the main two, and that is freezing point depression and boiling point elevation. There are a couple others, but these are the main two that we talk about in chemistry, and this is the main two that we're going to talk about today in class. And so what we have is, when we talk about freezing point depression, get this back, there we go. So we're talking about that the freezing point, say it's 0 degrees Celsius, when we add something, it goes down. And so when we have a boiling point depression, the boiling point, say, is at 100 degrees Celsius, and we add something, and the boiling point goes up. And all of these are due to intermolecular forces and the interaction between water and the solute in question. These are all interactions, not reactions. So this is all very interesting. Again, it's colligative means that we're looking at the bulk of the solution, not just individual molecules, but looking at the bulk. So let's take a look at intermolecular forces. We got four of these that actually affect the boiling and melting points and those interactions. The first one's hydrogen bonding. This is one of the strongest ones that we have. And basically we have hydrogen attached to an oxygen, and it's usually nitrogen, oxygen, and sometimes sulfur. And they add fluorine to this. So anytime we have a nitrogen that has a hydrogen, oxygen, sulfur, fluorine, and it says hydrogen, that can be attracted to another, another nitrogen, oxygen, sulfur, or fluorine. And basically, it's a lone pair. So what we have is that we got this oxygen with a lone pair. There's another one over here, but we're taking a look at this one. And hydrogen from another water molecule comes in, and there's an interaction. This is an lone pair anti-bonding interaction, and it is fairly strong. Remember, water is always has a dipole moment. And it's a slightly positive end that is attracted to the lone pair of hydrogen, of the oxygen, excuse me. And so this is the hydrogen bonding. Very, very strong. Next one is dipole-dipole, where we have, I'm going to draw a simple molecule that has a slight negative and a slight positive. Water, acetonitrile, it could be any shape, but just to give us an idea of what's happening, we'll draw like a little block, and the next molecule has this attraction where it is slightly positive, slightly negative, and matches. But there's no other interactions, no actually intermolecular switching of mixing of orbitals, anti-bonding or non-bonding. It's just a pure electrostatic interaction. The third one is dipole, instantaneous dipole, and that is when we have a molecule. I'm going to draw the electrons and a positive, and they're all kind of neutral, even out, so there's no positive, no negative, and there we go. So all sides are equal, but if we put something that is polar next to it, so we have a slight negative and a slight positive, what will happen is that these will rearrange so that the slight negative is up, so we get these positive charges near the up positive end, up to by the the partial negative charge, and the partial positive charge influences the electrons to come down to the bottom. So this is an instantaneous dipole. So it immediately occurs, and it will remain when we have this dipole in place. Once we take the dipole away, it switches back to this original configuration, and it's fast. Now, van der Waals forces is basically when we have two things come together Both of these are basically nonpolar. We have an electron, positive electron, positive, positive electron, positive electron. And what happens is that one of these will switch. So because they're constantly moving, so we end up with this becoming electron, electron, positive, positive, and that will introduce, and this will introduce a dipole here temporarily. It's one of the weakest forces, but it's also size dependent, meaning that as the size increases, the stronger the van der Waals forces are. More movable the chain is, higher the strength of the van der Waals forces. So those are 4 intermolecular forces. Now let's look at how it affects water. Now water has structure. Now even though in the liquid phase, we're going to have hydrogen bonding, and this means that hydrogen is interacting with the oxygens in the crystal, and we're going to have all these structure. All right, and it's going to go on in a three-dimensional, and it's three-dimensional. So water has a three-dimensional structure. I'm just showing it to you right now, and this prevents it from boiling because you got to break this interaction for it to boil. So what happens when we put like something charged, like sodium, and chlorine, say sodium chloride in, the water structure will rearrange itself so that it's going to be surrounding the oxygen. I should say water will rearrange itself so it surrounds the sodium, not oxygen. And here the chlorine will attract the hydrogen in an electrostatic interaction. It's not a hydrogen bond, but it's an electrostatic interaction because water since there's no other oxygen or nitrogen here, it's just the chlorine with a negative charge, you're still going to get this type of interaction. And it's going to form these structures. Now here's the thing. This is a fairly strong interaction, something that's highly positive to something with water. And what's going to happen is that to make it boil, not only you have to break these hydrogen and oxygen interactions, but also the oxygen and sodium or the hydrogen with chlorine. That takes a lot more energy, so the boiling point increases as it goes up. And to freeze it, that means you're preventing the mortar molecules from forming a crystal. You put something inside that water structure, it's going to break it up, and it's going to make it to get it to become crystal. You have to lower the boiling point. Or it's easier for it to become liquid when there's something in it. So looking from the other way, if it's solid and you got something trapped in there, as you raise the temperature, it actually makes it easier for it to melt. The freezing point is depressed or is lowered. And this is what we mean by water has structure. Now we're looking at something that's ionic, but if we put something that's nonpolar in there, the effect is the same. So acetonitrile, oops, that's cyanide. Let me put another C here. Here's acetonitrile. This is highly negative. This is partially positive. And what happens is that when water comes around it, it's going to the hydrogen is going to come to this end and actually form a hydrogen bond, and oxygen is going to come around this end. But this is a carbon. It's not going to form a hydrogen bond, but it's going to have this slight interaction that's slightly positive and slightly negative. So dipole-dipole interaction. And this is going to form a structure around the molecule and preventing the water from boiling or from freezing until you get a lower temperature. Now the effects are not that strong as with the ionic compound, but it is there, and this is what we're talking about. And last, for when you talk about something that's like benzene, benzene has this structure where you have electrons in the double bond, and it's a cyclic structure. I'm just drawing the double bond system that's around the carbon. We'll talk more about that later, but there is, and the electrons can be either above or below it. If you put a dipole, it goes up or down, and guess what? It's going to become more soluble, and it's going to interfere with the water's ability to boil or freeze. And this is what we mean by boiling point depression and boiling point freezing point depression and boiling point elevation. Don't make the same mistake I am. So the freezing point depression is this equation, and where this is the number of particles. Whoops, come on, stop that. In the molecule. M is the molality, and this is a constant. So what we mean by if it does not fall, C12H24O12 is a sugar dimer. This is polar, but it only when it dissolves in water, it does not break apart. So N is equal to 1. Things like sodium chloride, N is equal to 2. Calcium chloride, N is equal to 3. And same thing with sodium oxide. So how many ways are we going to break things up? It takes if this is going to be 1, 2, 3, 4, or whatever. Sometimes you can get 5 or 6. Now with the boiling point elevation, it's going to be the same thing. This is the amount, it changes. So with the depression, this is going to be delta T. The delta T is positive, but we're going to end up subtracting from the freezing point to get the final temperature. The boiling point elevation is actually positive. I'm going to add it to the boiling point, in other words, to find the new boiling point. This is a constant, and this boiling point constant is going to be constant for each compound. Again, molality, and the number of pieces. I'm going to stop here for right now, and I'll do the next slides as examples. Thank you, class.